Hey everyone! So in this video, I like to talk about solving trigonometric equations using Pythagorean identities. So we've encountered a few trigonometric identities so far, and recall that this word identity, well, it just means an equation that's always true, regardless of what we plug in for the variables. So an equation that's always true. And so we can use identities, we can use our trigonometric identities to rewrite parts of an expression or parts of an equation, and this can sometimes help us evaluate an expression or solve an equation. And so let's remind ourselves of what identities we've seen so far. So we've looked at a handful of equations we've called the Pythagorean identities. And there's many different variations, but the main one that comes from the Pythagorean theorem is if we have sine squared of theta, and we add that on with cosine squared of theta, this is always equal to 1, regardless of what value we plug in for theta. And so if we ever are dealing with an equation or an expression and we see a sine squared plus a cosine squared, we can replace that with a 1 because it always equals 1. We could also take this equation that's always true and rearrange the terms around to get another equation that's always true. And so if we subtract away cosine from both sides, we also get the equation sine squared of theta is equal to 1 minus cosine squared of theta. And so whenever we see a sine squared of theta, we can make the replacement with 1 minus cosine squared of theta, or vice versa. And we can also have, from our original equation, subtracted away sine squared from both sides to get cosine squared of theta is equal to 1 minus sine squared of theta. So these are all different versions of the Pythagorean identity, sine squared of theta plus cosine squared of theta is equal to 1. But there's actually more. And we can take our equation and divide both sides of our equation by the same number and still end up with an equation that's always true. And one thing that we can divide by is cosine squared of theta. Right, so if I divide the entire right side by cosine squared of theta, that means I would divide the entire left side by cosine squared of theta. And that means dividing every term on that left side by cosine squared of theta. And so here, sine squared of theta divided by cosine squared of theta, this is another way of writing tangent squared of theta. Cosine squared of theta divided by cosine squared of theta, well, that's 1, because any number divided by itself is 1. And then 1 divided by cosine squared of theta, this is another way of writing secant squared of theta, because secant is 1 over cosine. So this is another Pythagorean identity. Maybe shows it up a little bit less frequently than the other three, but it's still one to have in mind. And then one last one I'd like to include here is if we have that same Pythagorean identity, sine squared of theta plus cosine squared of theta is equal to 1. You know, here we made the division of cosine of theta from both sides of the equation. Well, we could have just as easily divided both sides of the equation by sine squared of theta. And when we do that, well, we get sine squared of theta divided by sine squared of theta, that's 1. Cosine squared of theta divided by sine squared of theta, well, that's a reciprocal or tangent squared of theta, so we can see that as cotangent of theta, cotangent squared of theta, that's the reciprocal function for the tangent function, is equal to, well, 1 over sine squared of theta, that's the same as cosecant squared of theta. Right? Cosecant is a reciprocal trigonometric function for sine. Right, so really we have 5 different identities here. And you know, I really wouldn't recommend that you remember all of them. You know, they really all come from this sine squared of theta plus cosine squared of theta is equal to 1. And so really, I would just remember this one and just know that you can build up all the others from this one identity. So another set of identities that we've talked about are the even and odd identities. Right, so one example is the fact that cosine of negative theta is equal to cosine of theta. That if we negate the input of the cosine function, well, we get the same result out as if we didn't negate the input of that cosine function. As for, well, for sine, if we negate the input of sine, well, that's really the same as negating the output of this sine function. So here we say that cosine is an even function, doesn't really care if we negate the input, and then sine is an odd function. If we negate the input, it's the same as negating the output. And then tangent, here tangent, if we negate the input, well, again, it's the same as negating the output, much like the sine function. It's an odd function. And so here, you can also think about these as describing how their graphs are symmetric. So an even function, the cosine function, for example, is symmetric about the vertical axis, and so that's really what this identity is describing here. Whereas sine and tangent are symmetric about the origin. You can imagine sort of rotating the graphs 180 degrees around the origin and you get the same thing, the same graph. Or you can imagine reflecting both over the vertical axis and the horizontal axis one after the other, and you get the same thing. And so these are the even and odd identities. These I would definitely want you to commit to memory. Another set of identities that we've briefly talked about are the co-function identities. Now these don't appear too often and they're not really worth storing in your memory, but if I have a right triangle here, and I have a side length of A, B, and a hypotenuse of C, let's say this angle out here, let's label it theta. What would that make this other angle in this right triangle? Well, 90 degrees of this right triangle, those are already accounted for, or maybe in radians it's pi over 2, it's already accounted for. And so we only have 90 degrees left over to be split between theta and this other angle out here. And so whatever this angle is, it has to be 90 minus theta, or if we write this in radians, we could write this as pi over 2 minus theta. It has to be the measurement of this last angle. And so if I look at sine of theta, right, so here's sine of theta, that tells me to compute the opposite side length divided by the hypotenuse. Well, notice that this is really the same as taking cosine of pi over 2 minus theta, right? If we take cosine of pi over 2 minus theta, well, we take the adjacent side of pi over 2 minus theta, this angle here, that's b, and then we divide it by the hypotenuse c. So really, in both cases, we're getting the same ratio, b over c. And in general, it's going to be true that sine of theta is equal to cosine of pi over 2 minus theta. And really, this is the same for all functions, all trigonometric functions and their co-functions, is that secant of theta is equal to cosecant of pi over 2 minus theta, and tangent of theta is equal to cotangent of pi over 2 minus theta. So these are another set of identities that may be useful. Again, I wouldn't store these right in the front of your memory, but they're good to know. So let's go ahead and use our identities to help us solve some equations. So I've got the equation 2 times cosine squared of x plus sine of x minus 1 is equal to 0. And our approaches that we've covered so far for solving equations don't really help us here. Right, I look at this equation and I don't see a way of factoring it as is, and it doesn't look like one of our basic equations that we can solve by isolating one of the trigonometric expressions. But one thing I do notice is that this cosine squared of x here, I know that that's the same as 1 minus sine squared of x, right? It's just a way of rewriting the Pythagorean identity. And when we do this, if we were to make this swap or to make this switch, well, we would have 2 times 1 minus sine squared of x plus sine of x minus 1 is equal to 0. And now this equation, well, the only trigonometric function we see in here is the sine function. And so maybe we can factor this. But before we can factor or try and solve this by factoring, we first need to simplify this left-hand side. And so when we distribute that factor of 2, well, we get 2 minus 2 sine squared of x plus sine of x minus 1 is equal to 0. And then combining these, this 2 and this minus 1, well, that leaves us with negative 2 times sine squared of x plus sine of x, and then here that's plus 1. So that's going to be equal to 0, or we're looking for when that is equal to 0. And if we're going to try and solve this by factoring, then typically it's simpler to factor when our leading coefficient is positive. And so it might be beneficial for us if we multiply both sides of this equation by negative 1. Or if the left side and the right side are equal, then they're going to be equal after we multiply them both by negative 1. And so when we distribute that negative 1, we get 2 times sine squared of x minus sine of x minus 1 is equal to 0. And if this is going to factor, well, I know I'm going to have a 2 times sine of x times just the sine of x. And if I'm going to get this factor of 1 here, or this constant negative 1 term, well, I should have a plus 1 and a minus 1 that are multiplied together. And because this middle term is negative, I know that I should get, in the rest of my product, more negative signs out. So here maybe I'll write this minus 1 here so that that minus 1 would get multiplied with this 2 times sine of x, and would give us minus 2 sets of sine of x. And I'll put a plus 1 here so that those two would combine to just a plus sine of x, and that would combine with a minus 2 sine of x as a minus 1 sine of x. And so here, that's our factorization, right? We've got the 2 sine of x squared, or sine squared of x. We've got the minus 2 and plus 1 sine of x to get that minus sine of x, and we got the plus 1 and minus 1 to give us the minus 1 out at the end of the day. So this is a proper factorization. And now, to solve this equation, we just have to ask ourselves when the factors themselves are equal to 0. Right? If we have two quantities multiplied to 0, well, that's only going to be true when either of the things you're multiplying together are 0 themselves. And so here we have 2 sine of x plus 1. When that is equal to 0, we get a solution to this equation. And when sine of x minus 1 is equal to 0, when that's true, we get a solution to this equation. And so for this right equation, adding 1 to both sides, we get sine of x is equal to 1. On this left side, we get 2 times sine of x is equal to negative 1, or in other words, sine of x is equal to negative 1/2. Whenever x makes either of these equations true, it's truly a solution to the original equation. And so I think the simpler one to work with here is this right equation. When the sine of x equal 1, well, right, sine of x gives us the y-coordinate on a unit circle. And so we're asking, when do we get a y-coordinate of 1 on this unit circle, this circle of radius 1? Well, that happens when our input angle is pi over 2, right? That's one candidate. Also, if we go all the way around the circle again, and end up at what is that? That's 5 pi over 2. If we add a full rotation of 2 pi to pi over 2, we end up at another angle that sine would give us 1 for. And so here we get the solutions. X is equal to, this is pi over 2, is one such angle, and then all the coterminal angles. In other words, any time we add on 2 pi or multiples of 2 pi, we get more solutions to our equation. And then here, sine of x is equal to negative 1/2. That's asking what angles give us a y value of negative 1/2 on this unit circle. Well, that happens at these two positions here. And so one occurs at when our x variable is 7 pi over 6, or all coterminal angles. And another solution occurs at 11 pi over 6, right? Pi over 6 shy of the full 2 pi rotation around the circle. And then here, whenever we have coterminal angles to 11 pi over 6, we'll also get solutions to this equation. So here, these three sets of solutions are all of the solutions to our trigonometric equation that we started with. So here I have another example. Cosecant squared of theta is equal to cotangent of theta plus 3. I want to figure out what values of theta makes this equation true. And here I've got two different kinds of trigonometric functions in this equation, so it makes it a little bit more challenging to try and solve this equation. But one thing we can do here is notice that cosecant squared, we have an identity for cosecant squared of theta. Right, if we take our Pythagorean identity, sine squared of theta plus cosine squared of theta is equal to 1, and we divide both sides of this equation by sine of theta. Sorry, not sine of theta, sine squared of theta. We get 1 plus cotangent squared of theta is equal to cosecant squared of theta. And so here, because we see that cosecant squared of theta, and we have a cotangent of theta in this equation, it might be helpful to make the switch from cosecant squared of theta to 1 plus cotangent squared of theta. And so let's rewrite that cosecant squared as 1 plus cotangent squared of theta, right? That Pythagorean identity is telling us that those quantities are the same, regardless of the value of theta. And so we can make this switch. And the benefit of this is that now this trigonometric equation is only in terms of cotangent of theta. I can try and factor this out by subtracting both sides by cotangent of theta. Right, so here maybe I'll write this as cotangent squared of theta. If I subtract both sides by cotangent of theta, I have minus cotangent of theta. I still have the plus 1 is equal to 3. And then I can subtract 3 from both sides to get cotangent squared of theta minus cotangent of theta minus 2 is equal to 0. And then here, for this to factor, we would expect a cotangent term there in the first term of that first binomial. I have cotangent of theta here. And we just want to figure out what two numbers multiply to 2 but add up to -1. Well, we can put a plus 1 here and a minus 2 here. Right here, if we multiply this out, we get the cotangent squared of theta. We get one set of cotangent, one positive set, two negative sets, combine those to be negative cotangent of theta, and then -2 times or positive 1 gives us the -2 out that we expect. Okay, so solving this equation now, we just have to ask when these factors themselves are 0, and so here we get one equation, cotangent of theta minus 2 is equal to 0. And another equation we want to solve is cotangent of theta is equal to 1. Oh no, sorry, I'm getting ahead of myself. Cotangent of theta plus 1 is equal to 0, right? We're asking when the factors are themselves 0. And so adding 2 to both sides of the left equation, we get cotangent of theta is equal to 2. And subtracting 1 from both sides of the right equation, we get cotangent of theta is equal to -1. So we want to solve these two equations, and any solutions to these equations are solutions to our original equation. And so here, we were dealing with the reciprocal trigonometric function. It might be simpler if we deal with one of our three main trigonometric functions, sine, cosine, and tangent. And so here, maybe let's write this instead in terms of tangent. So here I can write this as 1 over tangent of theta is equal to 2. And isolating tangent of theta, I would multiply tangent of theta to both sides to get 1 is equal to 2 tangent of theta. Divide both sides by 2, giving us 1/2 is equal to tangent of theta. And then for cotangent of theta is equal to 1, we can rewrite this as 1 over tangent of theta is equal to -1 or 1 is equal to negative tangent of theta, when we multiply both sides by tangent of theta. And then we can multiply both sides by negative 1 to give us negative 1 is equal to tangent of theta. And so here, this second equation might be a little bit more straightforward to solve. Right, this is asking us what angles theta, oops, can't draw a circle. Here we go, let's try one more time. So what angles theta have a slope of negative 1? That's really what that equation is asking us to figure out when we're trying to solve it. And so here we get a slope of negative 1 when we're at 3 pi over 4, or any pi, multiple of pi added onto that. Right? If we go halfway across the unit circle, we'll end up with another angle that has a slope of negative 1. And so here this occurs, we get solutions when theta is equal to 3 pi over 4 plus pi n. And then tangent of theta is equal to 1/2. Unfortunately, this doesn't coincide with any of our special right triangles or ratios of the side lengths of our special right triangles. Right, tangent of pi over 3 gives us the square root of 3, and tangent of pi over 6 gives us 1 over the square root of 3. Tangent of pi over 4 gives us positive 1. Really, this isn't one of our familiar slopes from tangent, and so here we will have to use inverse trig. Right, so this will tell us if we have inverse tangent of 1/2, we'll get an angle, but inverse tangent only gives us angles between negative pi over 2 and pi over 2. And so if we take inverse tangent of 1/2, we'll get an angle between negative pi over 2 and pi over 2, such that tangent of that angle would bring us back to 1/2. And so maybe just to include a picture here, what we're doing is we're saying, hey, we've got a slope of 1/2. Maybe that's a slope of 1/2, right? It looks kind of like it's up 1 and over 2, or at least very similar to that, very close to that. And so here, this angle would be inverse tangent of 1/2. Right, it's giving us that angle between negative pi over 2 and pi over 2, so between these two angles. But again, we get another solution anytime we're coterminal with this angle or on the other side of that unit circle. So here, really the solutions to this equation are, well, theta is equal to inverse tangent of 1/2 plus pi n. And we can approximate this using a calculator. And that's roughly 0.4636. And getting all the other solutions from this equation would amount to adding plus pi n onto this angle here.